Hi, my name is JP, and I work at Weaviate as a Senior Developer Educator. I'm going to talk to you today about how to turn all this amazing intelligence that's hidden in PDFs into an easily discoverable insights. So let's get underway. First of all, why PDFs? Well, PDFs are this amazing tool that is also surprisingly complex. Let's talk about what I mean by that. Here's a product manual that includes all these images and text. And actually, you'll be surprised when you dig into it how much information is really encoded on a dead image like this. And here's an image from a really old patent application for a plane. And look, it's just an image with 3 pictures. But if you start to think about how to decode this into a format that computers can understand, well, you'll see that perhaps the decisions aren't so obvious, right? There's a mixture of figures, multiple figures, images that kind of overlap each other in terms of boundaries. So is this one image, multiple images, or is it a collection of text and images that's blended together? It's an interesting one. Here's a very typical PDF report that includes a whole lot of text, really interesting graphs and figures, and a table on the bottom right as well. And you'll see that when we start to think about how to break up this particular page, that we'll need to make some decisions. Here's a very typical PDF format, which is, of course, a picture of a slide deck. And we've all seen across that. And it's very complex with a lot of intricate information that's encoded in it. And here's something that I personally have to read quite a bit, which is a screenshot from an academic paper. It's very dense with a lot of text, and the text part of it is relatively straightforward to parse, but it quite often, again, includes very interesting figures that add context to the text, and it'll include very dense tables and so on as well. So how do you go from these types of images and information to something that we can work with, and ultimately the intelligence, wisdom, and insight that we want to get from these images? So let's talk about some solutions and the challenges that they have. With existing tooling, text-only PDFs are relatively easy to work with, and that's because they have a fairly simple layout, which means they're easy to parse and convert to just blocks of text. So something like this with a mixture of code examples and text would be fairly straightforward to turn into a series of text items. And even the cover pages of papers would be fairly straightforward as well. So you can see there's different sections of it, sure, but there's not a lot of decisions to be made, perhaps, that are very difficult in terms of how to turn this image into blocks of text. But when you get to mixed media with different layouts, we start to get more challenging situations. So as we looked at earlier, when you have images like this, how do you decide what the boundaries of each text are? Is it 3 blocks of images? Is it 6? Is it 5? It's very difficult. And you also notice that the information flow here isn't straightforward either. You actually start from the top, you go through the middle, you go from left to right, and then you go down again, once again going from left to right. So deciding to break up something like this will depend on you knowing what the user is looking for beforehand, which you don't, of course, always know. And it's the same thing with these slides as well. Is this one image or is this a series of information? It's not really clear either. And as I alluded to earlier, something like this image, there's a lot of decisions to be made that again relies on you knowing beforehand what the task is, and you don't always know that either. I would say this maybe is made up of the cover text or the metadata, if you will, at the top of the image, and 3 separate figures. But even breaking up and identifying those bits of images and actually mechanically breaking up these images into 3 distinct images is not straightforward either. So here's a typical workflow with something like this. You go through document parsing, from after which you go and extract the text bits of the image as well as the actual images themselves. And you have to have some way of figuring out what the overall layout is. Once you've done all that, you might still need to chunk the bits of data that you've extracted, for example, on the academic paper, which is very, very dense. Once you've done all of that and have the layout, and the text components, you have to now rebuild all of this content into one coherent set of a content. And once you have the content, then you can work with it. And a lot of that is going to involve you performing searches, whether it's keyword searches, semantic searches, and so on. So here's an example layout using a very popular and very, very good library called Docling. So you start from a PDF, go through parsing, OCR to get text, figure out the layout of it. Oh, if there's any tables, you'll have to reconstruct that, and then you assemble all of those documents. And if you have that now very complex document object, you might then, for example, export that to a JSON, Markdown, and so on with, of course, figures. And once you have all of that, you can start to chunk maybe your data to perform RAG or retrieval augmented generation. And look, this is an excellent pipeline. It's an excellent library, but you can see there's a lot of steps, a lot of decisions to be made, and it's quite often going to be a solution that you need to bespoke build for your particular use case. So what are the challenges with this existing tooling? Well, as I mentioned before, it is quite complicated, right? You have to figure out where borders are between images and text. You have to figure out the relationship between these elements, and you have to know the context between all of these elements in between. There's chunking decisions to be made, and all of this means that you have to make judgment calls all the way along the process. And that also means that those judgment calls would depend on context, and having a one-size-fits-all solution becomes very, very difficult. So what might be a different approach than this kind of solution? And that's not to say that the previous solutions are not ideal, but can we do better, or can we do something different? I would argue that one really good solution is just to embed the whole page of a PDF. In that context, you would start with a PDF, and then you send it to an embedding model, and you just add that to a vector database, something like Weaviate. The only thing you would need to do then is to break up your PDF into its constituent pages, add those to the embedding model, and of course send that to a vector database. Why is this an appealing solution? And to discuss that, let's go back to the types of pages that we were looking at before. Well, one really good reason for it is that it respects the entire page layouts. And that also means that the data that we're working with is already chunked, right? Because when we're looking at a page of a PDF, naturally the page is laid out so that us as humans can look at the whole thing as one page. So it's already been decided by the author that this is the whole unit of information that we'll be looking at. And that synchronicity between how we look at the page and how we embed the information into a database actually makes a lot of sense if you think about it. Another really good benefit of this approach is that this is a very robust approach, right? Because we don't have to make these decisions about how to chunk up pages, how this information layout is put together and translate it. It's actually fewer steps for things to go wrong. And again, that means there's fewer room for mistakes and fewer room for misalignment between the task and the solution. So let's have a very quick demo of one such fairly simple implementation of PDF search. Okay, here's a demo app where I'll be searching through a slide or sets of slide decks that I've created in the past. I actually built this app for me because quite often I find myself looking through slide decks or thinking about previous slide decks I've made and thinking, oh gosh, I think I made a slide about this topic and I can't remember exactly where it is, or in fact, if I'm remembering it correctly, and whether I have slides like that at all. So I did exactly what we talked about and embedded each slide into an embedding and just added it all into a Weaviate database. So let's have a look at some demo searches and see how that looks. If I search for the words, say, Weaviate cluster architecture, I get these top results. The first one makes sense. It's got the words Weaviate architecture in it in the image. So the model's done a great job of identifying that. And it's also got some, cluster architecture diagram. So it makes sense. But what's really cool is that these other images don't have the words cluster architecture in it, or either of those words. But because the image is identified as it's some sort of an architecture diagram, right? And it involves multiple nodes and shards and so on, all these concepts related to a cluster, the model's done a great job of pulling those images up. And this works with all sorts of other concepts as well. So here's some images that come up when I search for the words memory savings and costs. So there's slides about scalability, examples of how much a technique called quantization helps you do memory footprint and so on, and that works really well. In fact, if I search for the words SpongeBob SquarePants, it actually pulls up these amazing slide decks that our colleagues built, which uses means or figures from the SpongeBob SquarePants as part of a story that he tells about vector databases. And again, this is not based on any kind of textual embeddings or metadata or anything like that. All of these figures are being pulled up directly based on what's on the image, whether it's words like you saw earlier, or just the concepts behind the images that are in the slide or the image itself. So that's a really, really powerful and great tool. So hopefully that demo was interesting to you. So let's talk about how all of that works. How does it work, and how is it that those embedding models can understand those images and pull up the right ones when we search by text? The model that I chose is an example of a modern multimodal model. In this particular case, I'm using a Kopali model, but there's other choices as well, like the Cohere Embed v4 and many, many others that'll do the job. What do multimodal embeddings actually do? Well, at a very high level, it can embed all of these similar ideas, whether it's an image of a lion, the words "lion is the king of the jungle," and this movie of a lion or an audio, all of these different modalities of concepts into essentially similar machine understandable vectors. So at a very, very high level, it's basically translating all of these concepts into the core embedding language that we can search for similarities for. And what that means is that, hey, you don't need to worry so much about the modality, whether it's an image or text or so on, but what it'll do for you is it'll embed those meanings or concepts based on how similar they are, right? So even if you have an image of a lion and those words that we talked about a lion, those two would be seen as being more similar than an image of a brass instrument, right? Because they are similar in concept, as you'll obviously understand by just thinking about them. So it's a very human way of understanding concepts regardless of the form of that information. And the distance between these close vectors and the far vectors will reflect how close they are in meaning. I'll talk very briefly about how these models work. Basically, all of these multimodal models start with specialist models, whether it's for text, images, and so on. And they perform this translation so that the similar concepts, regardless of modalities, get closer to each other. So again, similar vectors mean that they are similar in meaning, regardless of the original modality or the form of the information. And that's the thing, that's the magic that enables searching, whether it's text to any search, so you can search for the words lions roam the savannas, and you get all of these different information that are related regardless of the modality that they're in. And you can actually perform searches in any modality and retrieve information in any of the modalities, as long as that model supports that particular modality, right? So you can search by text, images, or even videos, and retrieve information in text, images, audio, and video, as long as the model supports those. So what does that mean in terms of retrieval? So as a user, you can type in or send in a query, whether it's an image or text, send it through the embedding model, and as long as that embedding model, from that constituent database, you can find the related concepts and get those results back without worrying so much about the modality of the information. More specifically, the model that we are using here is what's called the Multi-Modal model, as I mentioned, and that's very specifically related to the way that works is that it breaks up an image, like this example of an academic paper you see here, into a set of patches. In other words, it's saving information from different parts of an image and saving the meaning from that. And it goes through the same kind of embedding process as in your text model. And when you perform a query, it's able to look at all these different parts of an image as, again, you would as a human retrieve the right parts of the information for you. So, and these patches can be divided up. This is showing just 4 patches per image, but in reality, you're looking at hundreds or probably like 1,000 patches per image. And as an example, this is an example that they use in the Multi-Modal paper. When you have an image like that and you run a query, hey, which hour of the day had the highest overall electricity generation? This heat map shows a correlation between the word or the token hour and what parts of the image that it's highlighted. So it's actually the models recognize that the x-axis, which shows the number of hours, correlated very highly with the query term hour. And you can also see the same thing with certain parts of the image, like the top header where it talks about hourly generation. So putting all of that together, Multi-Modal models are able to retrieve the right vectors or the right image back for your query, even though the image is made up of a lot of information, like depicting different parts of it, including text and so on. It's very, very impressive. If you're new to multi-vector type embeddings, I'll just go through that very, very quickly. Typically, if you're looking at a single vector embedding, you'll get something like what's shown on the left-hand side of this image. If you have a text like, hey, you're a wizard, Harry, each of that bits of text gets broken up into what's called a token, and each of those tokens get saved as a vector before they get concatenated, so not concatenated, but pooled into one output embedding. But in a multi-vector embedding, what happens is that each token would get turned into a vector, and the output embedding would capture all of those individual vectors, respecting their constituent vector meaning. So the trade-off typically is that the output embedding of a single vector embedding kind of squashes, for the lack of a better word, all the meaning together by pooling methods. And in a multi-vector embedding, the meaning of those words or tokens are preserved. So you can imagine that these are typically going to be a little bit larger. So even though individual vectors of a multi-vector embeddings tend to be smaller because you're saving a vector per token or so, you end up with larger vectors here. In terms of image embeddings, each patch that we talked about ends up acting similar to a token. So each of these patches get converted to an embedding and saved. I'm sure you have some questions about what that means for sizes and scaling, so let's talk a little bit about that. In terms of a multi-vector embedding, especially with images, it's actually quite common to have very, very high number of dimensions, like 100,000 dimensions. For context, typically for a single vector embedding, you get about 1,000 to 2,000 types of tokens. So what that means is that embedding tokens, also embedding images, as I talked about in this demo and this talk, you're going to get embeddings that are 50 to 100 times larger than what you might be used to seeing. And that, of course, is going to present its own challenges, right? So one solution to that is quantization. So with quantization, you can of vectors, you can reduce the precision of individual dimensions of a vector, right? So in this example of a multi-vector embedding, you can see that the individual numbers or the individual dimensions you see in the graph, in the chart, is reduced in precision. So with binary quantization, all of these floating point numbers become a binary. Or for scalar or product quantization, the precision of the individual dimensions get reduced down to an integer, saving you, again, lots of memory. But there's also other cool techniques that we can apply here as well. Something that we've been working on implementing at Weaviate recently is this Movera encoding technique. What Movera does is really, really cool, but at a very, very high level, it applies a transformation so that these individual vectors or the multi-vector embedding gets concatenated at the end of the day into a slightly longer than a single vector embedding, but shorter than a multi-vector embedding. So that has a lot of benefits, like in terms of the memory footprint of it, but also you end up with a one vector, so your search ends up being faster generally. To make that a little bit more concrete from a user perspective, here's some memory footprint of a multi-vector embedding, looking at Movera encoding on the second, third, and fourth images versus just the raw multi-vector embeddings on the left. So in this particular example that we ran in-house, you're looking at about 30 gigabytes of RAM usage for a particular data set. If you apply Movera, you're looking at only 5 gigabytes, which is amazing, and it's a 70-80% reduction with doing very little work otherwise. And if you apply quantization on top of that, you can actually go down even further, and you're looking at about 3% of the original memory footprint by reducing this size. I've noticed speed advantages. There's another really big advantage with using Movera, which is the import time. So because the multi-vectors are very, very complex, it can require a lot of processing to import all this data into your database. But again, with something like Movera, you can reduce that import time taken from something like 20 minutes or 25 minutes or so to 3-4 minutes. And just even adding quantization will add a little bit of time because of the additional compute involved, but you can see that overall it's still a very small fraction of the original. Now, I will say that this isn't going to be entirely free. Of course, there's some costs and trade-offs that you need to make when you're applying techniques like this, right? So what's the cost? Well, one is, the big one to consider is a slight degradation in search quality. I mentioned search speeds, and you'll see that in this graph here, which notes the queries per second or throughput of how many searches you can do in a second. The blue line shows the no Movera multi-vector regime. And that you can see is actually a bit slower than the ones where we applied Movera. But that's not actually a fair comparison necessarily, because if you look at this next graph, generally the recall or the search quality, or how many of the relevant results you want are found in the search, goes down. So at the same set of parameters, so I'm using an EF parameter as an example here, the search quality goes down. So if you want the same search quality at, say, of 0.9 or 0.8 recall, you'll see that we have to move much further along to the right in the graph to get the same result recall with Movera. So that's going to be a little bit of a trade-off as to how to get the same search quality with Movera versus without. But we can we even do more than just perform searches with these PDF images and so on. So let's go back to our demo. Okay, so here's the same demo app that we looked at. Let's go back to a search about Weaviate cluster architecture and run that. And I'll note that this is all running live on my laptop. So we found these Weaviate architecture diagrams. But what does that mean? Can we do something with it? Well, I'm sure you're familiar with RAG, or retrieval augmented generation. And you might not be surprised to hear that actually you can perform RAG with all of these images. So here's a RAG response using a vision language model. And I've just given it a stock question of, hey, what do these slides tell us? The user wanted to find out about Weaviate cluster architecture. And the model gives a very good response when all we did was just pass this prompt and these images that we found above. It says, oh, here's the information about cluster structure, data management, metadata, and so on. So it's able to read the information from those PDFs and inform us what's in them based on the context of our question. And we can do the same thing about memory savings and cost. So I talked about quantization earlier. So now once we find the right slides here, We can pass that information to the vision language model, and let's see what it's going to tell us. Here we go. It says, okay, the slides discuss scalability and memory usage. So it talks about exactly what we talked about in terms of memory usage. And it's able to even do a really good job of reading the graphs and reading the numbers in it. So it says if you just use HNSW in this demo, it used 6 gigabytes of RAM under the particular scenario. And using BQ or PQ, reduced the memory footprint to about a third of that. And again, I'd like to highlight that I've not passed any other information than these graphs and the prompt to our vision language model. And to me, this is really impressive. And again, I can get not just the raw data that I need, but I can extract actionable information because I can get my questions answered about, oh, what do these slides tell us? And transform the information that is in our database. So what's happening here in this system? Well, the short answer is multimodal RAG or retrieval augmented generation. I'm sure you're familiar with regular RAG or retrieval augmented generation, where you pass a query or so to a database and you get the results back, and then you send those results and the prompt into a foundation model like a large language model and get some response back. Well, multimodal RAG works very similarly in that now what you're doing is to get the results back that are not just bits of text, but also objects of different modalities, right? So now you can pass those results into a foundation model that can do something or understand those types of information. And as you saw earlier, just now, we can get extracted information that answers our question for us. In some models, I'm sure you won't be surprised to hear, the response can also include generated images and multimodal data as well, so quite typically images. And this is a really cool innovation, and I'm sure we're going to see more and more of going forward. So if you're working with something dense like PDFs and so on, this is the kind of stack I would use and I would probably suggest. I think the easiest thing that is like most robust and not brittle is just embed the entire image or each entire image into an embedding model and save that into your database. And then you can apply a RAG pipeline on that set of data and get the results as you saw in the app. And for me, the advantages of that are the less brittle nature of it. And when you work with that information or with that pipeline, it makes it easier for you to concentrate on what adds value for you, which is to extract easier insights from your data and so on. What I really liked about this demo or building this demo was that because I got to work with Weaviate, I got to abstract away a lot of problems that I would have to normally figure out how to do. So here I didn't have to deal with how do I pass my image or images that I found to a foundation model to get responses? How do I manage my data in my database to make sure I get the right objects and send it to the model and so on? I was able to concentrate on building this app, so it would be very interesting or as interesting as I can make it, hopefully. And also just getting the right results shown on the application and managing the data in the database and working with foundation models was all abstracted away for me. And some of the other details that I showed you in terms of working with embedding models and optimizations like Movera and quantization and so on is all taken care of by this database, which is really nice. And if you want to then go to production with this type of system, the database scaling, like how does the indexing work and sharding work, is all taken care of for you as well. And that's one of the things that I highlight when I talk about systems like Weaviate is that the developer experience is just top-notch. So I hope that was really interesting and whet your appetite a little bit about working with multimodal models and some easier ways of working with really rich sources of information like PDFs. If you want to learn more, the app is available online at this GitHub address. We have additional resources as well, like this Weaviate Academy course on working with multimodal data. We have a course on deep learning AI, which is amazing, with our colleague Sebastian. And the Weaviate documentation, of course, if you want to actually work with Weaviate. Thanks for watching. I hope you found the talk interesting and I hope you enjoy working with multimodal data and working with Weaviate. I think it'll add a lot of value to how you work with your information and rich sources of data like PDFs. If you want to contact us or find more information, here are some useful links. And also, I'm on LinkedIn as well if you want to reach out and say hello. Thanks very much, and I hope you enjoy the rest of the conference.